We are now beginning Module 6 of Hydrogeology. This is the second half of the course now. In this module, I'll talk about the geologic occurrences of groundwater, and I'll begin in this video with glaciofluvial environments. In this video, and the videos to come for this module, I'll talk about several examples of groundwater and its geologic setting. We'll start with the Puget Sound region, then take a tour of the Basin and Range province of Nevada, move on and spend some time on the Columbia River basalts, which lie to the east from Seattle of the Cascade Mountains. I'll talk about coastal aquifers in general, and then consider Florida and its aquifer system. There are additional examples of aquifers and their geologic settings in the textbooks. For all of these geologic settings, there are certain characteristics that I want you to pay attention to. The geology in particular. How were these structures formed? What kind of structures exist in which water now flows? Are there any other unique geologic aspects to these aquifers? What are the aquifer formations? What are the aquitard formations? What are the flow regimes within these aquifers? Do you see simple local flow, or is there a regional component? Are the aquifers confined or unconfined? What constitutes the hydrologic balance for these different examples? What are the sources of recharge and discharge? How does storage change over time? And then, of course, there are the societal issues. What are the current usage and contamination issues? What other current events are associated with these various geologic settings of aquifers? Let's talk about the formerly glaciated regions of the United States to begin with. In particular, we're going to look at what were locations that lay on the margins of the great ice sheets. And this region extends from the Pacific Northwest across the Midwest and across the Northeast. We'll focus primarily on the Pacific Northwest with these discussions. There are some local resources that I would like to draw your attention to. And at the University of Washington, we have had a very active research group called GeoMap Northwest. I've given their website. Unfortunately, they have an operation suspended as I make this video. Their website is still active and the resources are still available. Now, King County has a very nice set of groundwater web pages with the availability of all kinds of data for download. Washington State has two sites of interest. The first site I have here, the Fortress site, has a database of subsurface geologic information. And the second site from the Department of Ecology is a database of well logs and well locations across the state. Here's the homepage for the King County groundwater resource information, and as you can see looking at this, there are groundwater data available, maps and reports, discussion of management areas. It's a very comprehensive site of information relating to groundwater in the local King County region. Let's jump into glaciations. I have a plot here which represents glacial history over the last 2 million years. And let me walk you through this. This is a record of continental scale glaciation and interglacial periods, expanding a time from the present back to 2 million years before present on the vertical axis. The horizontal axis is a record to the left of increasing amounts of ice and to the right decreasing amounts of ice. ice on land. This is obtained from the oxygen isotope ratio in deep sea records, and I'll talk later in the course about how the oxygen isotope ratio gives a record of the amount of ice on land. But for now, let's just take it for granted that more ice lies to the left of this plot and less ice to the right. So as you go from the center line in the leftward direction, the graph indicates greater degrees of coverage of ice on land and less water in the ocean. On the right side, it's less ice moving in the right direction, and if you look at the top of the plot, you see that we are currently in an interglacial period in which there's very little ice, and so the current oxygen isotope is on the right side of the plot. Now, what's interesting is that this plot going back 2 million years shows a very extensive record of increasing amounts of ice on land and decreasing amounts of ice on land. The glacial cycle over the last 700,000 years has involved some extensive amounts of ice on land at time periods of about 100,000 years apart. So you can see going back every 100,000 years there was a peak in the curve. Now going back before that, in the period back to 2 million years before present, there's a period in which the cycling was shorter. It was about 43,000 years between glacial max. So the net thing on this plot is that there have been many glaciations over the last 2 million years. Not just one, not just a couple, but maybe 20 or more. So these advances and retreats of glaciers across the northern portions of the United States have left a complex record of deposition and erosion, and we'll look at that now. Let's see, here is a representation of the maximum extent of ice which occurred about 18,000 years before present, and you can see the major ice sheet centered over North America was in Canada. It stretched down through the Midwest, covering the Great Lakes region extensively and coming down across New York and not quite reaching Washington, D.C. On the far west, Cordilleran glacial ice cap, and it was not quite in phase with the Laurentide ice sheet. It reached its maximum 15,000 years ago. So in fact, the Laurentide ice sheet was already retreating when the Cordilleran ice sheet was expanding, and it expanded south down the Puget Sound to south of Olympia. Let's look at the kinds of deposits that ice sheets leave behind as they expand across the country, and then as they retreat, they drop off all the debris. So glaciers are conveyors belts that are easily capable of moving rock fragments from very large to very small. As the glacier then finally retreats, whatever rock fragments are on it at the end get left behind. So this picture shows stagnant ice as the water retreats. You see that there are marginal streams and lakes, and coming out of the mountains, deposition of material from mountain streams leaves behind deltas in the lakes at the edge of the ice sheet. There's debris on the ice sheet, and the ice leaves behind a pile at the very end where they've, in conveyor belt fashion, dropped it off in an end moraine. So as they retreat, they leave behind a record of the load as they melt. So take away the ice, and the shallow surface has a collection of deposits with different names that are illustrated here. There are end moraines that record the maximum extent of the glacier. There are deltas along the edge. Kames are the deposits in the lakes alongside the glaciers. There are eskers, which are deposits that were laid down in streams running between the surface, the earth surface, and the ice. So the channels in the ice got chocked filled with gravel. Kames are the deposits of a stagnant ice. So you have the water on the ice. The water has sediments in it. The sediments settle into ponds in the ice. The ponds collect the sediments, and then as the ice melts, it leaves the pile behind. Kettles in this diagram are where blocks of ice sat on the Earth's surface and depressed the Earth, caused local deformation that left behind holes that are often filled with water to form lakes. Let's look at a modern analog of a continental glaciation. If we go to Alaska, we can find large valleys with the glaciers at the head, and you see these large valleys are chock-a-block full of gravel. The glaciers have ground the gravel up from the mountains behind, and the rivers have transported it across the valleys. So this is called an outwash plain, and it's a contemporary glacial landscape. So there is a seasonal flow in the water here, and so the water changes in its capability of carrying the rock and gravel. When the discharge is large, very large material can be moved. When the discharge decreases, the load is dropped and fills the channels. So braided streams represent a constantly changing discharge, which will fill a section of stream and then occupy a new section of the outwash plain. So just imagine such a scene at the toe of the glaciers during the last ice age, leaving behind a record of sand, gravel in enormous outwash plains. So there's the braided streams, water level varying, and gravel dropped. Okay. Let's look at another example showing a heterogeneous nature of depositions associated with glaciers. Here you have a glacier that is retreating and leaving behind an end moraine, and to the right is a very large outwash plain from another glacier. So the outwash plain is filled with a variety of sorted sand and gravel. Sorted meaning the fluvial transport has graded the material from fine to coarse depending on how fast the water was moving. Where the water was not moving at all in the lake, very fine grained materials settle out. And in this lake here, there's fine-grained silts. In between, you have a moraine which has unsorted material, very large to very small. The material that is well sorted then becomes our potential aquifer material. The unsorted material becomes a potential aquitard. Silts and clay also become aquitards. Cross-sections through a landscape of glacial deposits shows some portions that may look somewhat layer cake, but then there are large deviations from the layer cake associated with eskers, moraines, drumlins, and so forth. And you see that there are regions of clays from lakes and till from glacial transport and sand and gravel from outwash. Here's an contemporary example in Alaska of mixed till and fluvial deposits. If you look at this hillside, you'll notice a difference between the deposits near the top and those lower down. This is a modern outwash capped by till. So where is the till? Up there. You see the till, it's all very unsorted, large and small, no structure whatsoever. Then there is a dividing line, and below that you see outwash, and it varies from large material deposited in channels to material deposited on point bars of braided streams. Looking at such a material more closely, you can see on the top it has very little indication of sorting. It's all just a jumbled mess. As you move down through this, you'll see more indications of layering, where there's a concentration of larger cobbles in one region, or a concentration of fine-grained materials in one pod. This picture is mostly shown to give you an idea of heterogeneity that is associated with glacial fluvial deposits. The heterogeneity exists on the very large scale, and it exists all the way down to intermediate and smaller scale. Coming closer to home, here is a typical view on any bluff around the Puget Sound region. You look at the bluff and you see something like this, and what are you looking at? Well, this is Vashon Age, and I'll talk about what Vashon Age means, outwash, capped by till on Maury Island. So let's look. The till is up at the top, and you can see that there's no structure, no sorting of that. There's a separation of the till, and below that is outwash. And if you look at the outwash, there's some appearance of layering of and fluvial sorting of the material. Elsewhere in the Puget Sound, this is on the south end of Whidbey Island, you can find massive layers of outwash, well sorted. You see all this material is sand, a millimeter-sized sand grain, and it's almost 400 feet thick from the water level up to the top of the bluff. So now, here is a generalized cross-section through glaciofluvial deposits. This generalized cross-section applies in the Puget Sound region. It applies in regions of Wisconsin, Minnesota. It applies across the northeastern states as well. You have less than layer cake appearance. You have layers, but the layers are not laterally continuous. You have till deposits, you have basal tills and bouldery tills and fluvial deposits, and they're all mixed up in a complicated fashion with erosional features and then later deposition on top of those erosional features as further ice ages occurred and new rounds of both erosion deposition occurred. So the sorting is variable from these different units. There's complex and non-planar layering. Some of these materials are excellent aquifers, some of them are good aquitards. Nothing, though, is necessarily large in aerial extent because the deposits do not extend over wide regions. Now let's talk in particular about the creation of the Puget Sound landscape. Here's a map of British Columbia extending down into Washington State. It maps the size of the ice sheets at various times, and if you look at this, about 25,000 years ago, the ice along the western Cordillera were mostly confined to the mountains and not extending out as large continental ice sheets. However, by 15,000 years ago, the ice had spread out from the mountains and pushed down into the Puget Sound. So this lobe pushing down through Seattle is sometimes called the Puget Lobe. Let's see, glacial max was 18,000 years ago, but Puget Sound was ice-free 18,000 years ago. The last major advance of ice in our area went down to just south of Olympia, and it's described as the Puget Lobe of the Fraser glaciation. So the Fraser glaciation is the last large expansion of the Cordilleran ice sheet, and the very last pulse of that ice sheet down is called the Vashon Advance or the Vashon Stade. So Seattle was ice-covered 15,000 years ago, but it was completely ice-free by about 12,500 years ago. So let's walk through what the steps were in creating the landscape we see today. Prior to the last glaciation, the Puget Sound did not exist. Imagine this whole area depicted in this picture, and by the way, this is a digital terrain map that is color-coded by elevations. So blue is mean sea level, and yellow is close to sea level, and then it ranges from deeper shades of red up into the mountains. River drainage at the time before the last glaciation was to the north. There were no saltwater arms here, but there were a series of rivers from the Olympics and the Cascades carrying water northwards to an exit through the Strait of Juan de Fuca. Then ice advanced during the Fraser glaciation. About 20,000 years ago, it expanded far enough south to start blocking off the northern end of the Puget Sound region. So a lake formed between the ice to the north and highlands to the south of Olympia. So this area filled up with water because the ice dammed the drainage pattern for the rivers. So the entire Puget lowland was covered by water. And as the water rose to a sufficiently high level, it began to spill out south of Olympia and then down to the Pacific Ocean in the neighborhood of Hoquiam. So, entire Puget Sound lowland covered. This lake then was a settling basin for all the fine-grained material coming out of the glacier, and so clay settled out to fill the basin. And eventually the lake was entirely filled with this fine-grained clay and silt. We call this layer the Lawton Formation in the Seattle area, and it's given the geologic term QVLC, Q for Quaternary, V for Vashon. So this was a Vashon state of the glaciation and the Lawton Clay Formation. So once the lake filled and the clay existed all the way up to the mean water level, streams extended from the glacier across this large valley and continued to exit to the south. So the basin became essentially a braided stream channel for the outflow from the glacier. It was a massive outwash plain. So sand and gravel, the outwash, were deposited across the entire area. The geologic term for this deposit is QVA, or Quaternary Vashon Advance deposits. Advance because these deposits occurred as the glaciers were advancing from the north to the south. In the Seattle area, the sand is called the Esperance sand. Eventually, the glaciers advanced south of Olympia, and 15,000 years ago, the Vashon state of the Fraser glaciation, we had ice over 3,000 feet thick over Seattle, and as the ice moved across the region, it left a carpet of till called the Vashon Till, or QVT. Beginning about 13,000 years ago, the ice began to melt. Large outflow channels formed between the ice and the underlying surface. These channels become eventually the major waterways, but initially they're just simply channels for large amounts of meltwater to flow under the ice and to exit down to the Pacific Ocean. As the ice melted, those channels were left behind and formed the main channel of Puget Sound and Hood Canal and various other channels that are highlighted here that were filled with salt water immediately after the glaciers retreated. But many of these channels were filled by sediments carried down from rivers from the mountains, and by 5,000 years before present, we reached a situation like we see today, where we have land in the Puyallup Valley and extending from Tacoma up to Seattle along the Auburn Valley, and Everett is dry land, and it stays dry land up to the north of Everett and out in the Snohomish River Valley. Okay, so standing on any hill in Seattle or anywhere along Puget Sound, you have a vista such as this, and all of this material that you see is the advance outwash plain from the Vashon state of the Fraser glaciation. We think of this as the Great Lowland Fill. It just filled up the whole Puget Sound Basin with clay, then sand and gravel to the top of the highest hills in the Seattle area. So if we look at the stratigraphy, and stratigraphy is just the layering and the geologic terms associated with the layering, here's a cross-section through Magnolia Hill on the west side of Seattle. At the top of the hill and all the hills around the Seattle area, you can find in places the Vashon Till. It's not continuous, it's been eroded away in some areas, but the Vashon Till drapes across the topography. Below the Vashon Till is the Vashon Outwash, the QVA. Below the Vashon Outwash is the Lawton Clay, or the QVLC. And below the Lawton Clay in Seattle is a QOB, which is an Olympia formation. It's a pre-Fraser glaciation set of sediments. And below that are many other sediment and till layers from prior glaciations. If we look elsewhere in the Puget Sound, here's a cross-section in Vashon Island. Here's what it looks like. It's not nearly so layer cake, although QVA and QVT drape across the top. The thickness of the outwash is highly variable because it filled in pre-existing valleys and channels on the landscape prior to deposition. And below that are a whole slew of different glaciofluvial deposits. Some are tills, some are fluvial, some are fine-grained, some coarse-grained, some are well-sorted, and others not. These other deposits range in age from tens of thousands of years to hundreds of thousands of years old. QVA is the common aquifer on Vashon Island and elsewhere in the Puget Sound region. Looking over a larger region of Vashon Island, here's cross-section extending from midway up the island to the north end. You can again get the sense that although there is a general layering of younger material on the top and older material down below, none of the layers are exactly continuous, and as you get to the older materials, they appear as pods here and there. Okay, let's look at groundwater in this glacial fluvial environment. On Vashon Island, I have a plot here of the hydraulic head in the QVA layer. And so the hydraulic head is plotted at 50-foot intervals, and you can see that there are two large pods of water, one on the north part of the island and one on the south part of the island. Running between them is Judd Creek. Looking at these contours, you can see that flow goes perpendicular to the contours. So there's flow from the high area on the north end of the island towards Judd Creek. There's also flow to the east out into the Puget Sound on the eastern side of the island, and there's flow to the west into Puget Sound on that side. So there's flow radially outward from these elevated areas of the hydraulic head. On the other one, on the southern end of this, you have flow into Judd Creek, and you have flow to the east and flow to the west. East King County also has outcrops and thicknesses of QVA, and this is an area between Duval and North Bend. And I'll focus in on the area between Duval and Carnation, where the highlighted area is again a QVA aquifer, and the contours here are in 100-foot elevations of hydraulic head. And you can see that water sits in this elevated region and it flows out and down to the adjacent valleys. So the Puget Sound aquifers. The shallow aquifer extends from near sea level to the highest portions of the Puget Sound Basin, which are in the neighborhood of 400 to 500 feet. Esperance sand, or Vashon outwash, QVA, is a typical aquifer material. It's a well-sorted sand. It has good transmissivity. It has high porosity. If there is no overlying till, the Esperance sand can make an unconfined aquifer. It's confined when overlain by till that forms an aquitard. Bounded below by the Lawton clay or other interglacial deposits like the Olympia unit or any number of pre-Fraser glacial deposits which can be till, outwash with variable age. The Puget Sound shallow aquifer tends to have high transmissivity. Recharge is local. The age of the water is quite young, and because it's local recharge and fairly rapid recharge to discharge times, contamination is a problem. So a typical value for the hydraulic conductivity in the QVA is more than 10 feet per day. In the clay, the Lawton clay, the hydraulic conductivity tends to be less than 1/100th of a foot per day until the vertical conductivity is 5/1000ths of a foot per day. Now the till does seem to have a higher horizontal conductivity. So discharge from the shallow aquifers tends to be in springs at contacts with the Lawton clay around the Seattle area, or it discharges into local streams, or in some places directly in the Puget Sound. Below the QVA aquifer, there are deeper aquifers extending from near mean sea level to hundreds of feet or even thousands of feet below mean sea level. On Bainbridge Island, water is produced from 1,200 feet. The geologic units associated with the deep aquifers can be the Olympia or other pre-Fraser, sometimes undifferentiated, unidentified formations. These are typically more heterogeneous than the QVA and are not typically regionally extensive. Recharge in the deeper aquifers is slow, and discharge tends to be sub-Puget Sound. The water is clearly older in age than that found in the QVA. Interesting fact about the Puget Sound aquifer is that they are closed with some exceptions. Closed means they cannot be drilled and tapped for water production in general, unless you are a municipality, a governmental agency. The exceptions, though, are given in various government handouts, exempt groundwater use for Washington, and both of these documents are found on the website for the course, and in the last week of the quarter we'll talk about them in more detail. So that ends my discussion of glacial fluvial regions. Coming up next, I'll talk about the basin and range region.